In the next example problem we're going to work through for this course, we are told that we enter a 100-meter long tunnel driving at a speed of 30 meters per second. And the moment we enter that tunnel, there is a cow on the opposite end of the tunnel that just steps into the tunnel, and that cow begins walking towards us at a speed of 5 meters per second. So on a picture here, I drew us entering the tunnel on the left, and the cow is entering the tunnel on the right. So we are moving at a speed of 30 meters per second, and the cow is moving towards us at a speed of 5 meters per second. Now, the question is, how much must you decelerate to barely avoid hitting the cow? So if you think about what's going to happen in this problem, there are two possible scenarios. You slam on the brakes, your car comes to a stop, but your car doesn't come to a stop before it hits the cow. So you hit the cow while you are still moving before you came to a stop. Or you slam on the brakes, the car comes to a full stop, and sometime later the cow walks into your car. We want to avoid the first case. If we come to a complete stop and then the cow walks into us, well, the cow is at fault legally, and that is not our problem then. But if we're moving and we hit the cow while we're still moving, that's bad. We want to avoid that. Now, the problem uses the word decelerate. Decelerate sometimes comes up, it's just a colloquialism. It basically means acceleration where you're slowing down. Often the word accelerate is usually associated with speeding up, but technically speaking, acceleration is a change in velocity. So acceleration could mean speeding up or slowing down, basically a change in velocity. Decelerate generally means you're slowing down. So here I drew a picture. We are approaching the cow moving to the right. The cow is approaching us moving to the left. And we're told the tunnel is 100 meters long. So I'm going to set up a coordinate system. I'm going to choose where x equals 0 is located, and I have to be consistent with all my positions after that. So I'm going to choose x equals 0 is the initial position of our car over here. And once I choose this location to be x equal to 0, immediately that forces right here to be x equals 100. Now, we are told that the cow is going to just be walking towards us at constant speed. But we are allowed to change our velocity. We are allowed to accelerate. In this problem, we have two objects. We have the car and the cow, and we will want to track the trajectory of each object. So I could talk about the initial position of the car, the final position of the car, the initial velocity of the car, the final velocity of the car, the acceleration of the car, and time. I could also talk about the initial position of the cow and the final position of the cow, and the initial velocity of the cow, and the final velocity of the cow, and the acceleration of the cow, and time. The thing is, time in this course is not affected by motion, so whatever time it is for the car will be the same as the time for the cow. So I'm just going to put time in between the two because it will be common to both of them. Now, as of the way this picture is drawn right now, are there any numbers we could immediately plug in? Well, the initial position of the car, when I enter the tunnel, and the entrance of the tunnel where I came in is at x equals 0, that immediately set my initial position to be 0. And that immediately set the initial position of the cow to be 100. I'm using subscripts car and subscripts cow to designate between the two objects that are moving. The final position of the car and the final position of the cow, at this moment, I don't know what they are yet. The initial velocity of the car, we are told, is 30 meters per second. We are moving that way. The initial velocity of the cow. Take a minute, think about what it should be. Pause the video if you want to. The initial velocity of the cow is -5 meters per second. Remember, the way I drew this coordinate system, to the right is the positive direction. The car is moving to the right, so the car has a positive initial velocity. The cow is moving to the left. So because right is the positive direction, the cow initially has a negative velocity. We are told that the cow is just going to keep walking at a constant velocity. It will never change how fast it's walking. So that means the acceleration of the cow is going to be 0. The acceleration of the car is ultimately the thing we want to find. So I'm just going to say that is really what we want here. We also will demand that our car has come to a complete stop just before it hits the cow. So if our car came to a complete stop, that implies the final velocity of our car is going to be 0. Well, final velocity of the cow, it never changes, so it will also be -5 at all times. And let's look at what we have written out right now. We have the initial position, the initial velocity, the final velocity, the acceleration of the cow. We really want the acceleration of our car. Let's think about the final position of the cow and the final position of the car. And let's consider several different scenarios. In scenario number 1, what if my car came to a complete stop right here and the cow was over here? When my car came to a complete stop, you could look at this picture and you could say there is some distance between us, so this is okay. What if my car came to a complete stop here and the cow is over here? Well, I look at this picture, there is a shorter distance between us, but I still have come to a complete stop before I hit the cow. This is still okay. What about this scenario if my car came to a complete stop and the cow is barely not touching the car? So here, there is literally 1 atom between my car and the cow at the moment my car has come to a complete stop. Well, this scenario is still okay because even though that distance is super duper tiny, I still came to a complete stop before I collided with the cow. That is what I must do. So this is still okay. Now, if I had traveled 1 atom further, a small infinitesimal amount, at that point I'm not okay because then I was moving when I collided with the cow. So we could say that the maximum limit, the maximum possible distance between that it takes the car to stop will be the moment when the car is barely at the same location as the cow. If I had traveled 1 atom more, at this moment, the cow and the car are separated by 1 atom, 1 infinitesimally short distance, and that is okay. And for all intents and purposes, I could say at this moment, the position of the car is basically arbitrarily close to the position of the cow. It's 1 atom separated. That's practically nothing. So we could just set these two equal to each other, and if I am under the understanding that I have come to a complete stop, this is still okay. So the final position of the car and the final position of the cow, I will set to be the same thing. If I slam on the brakes really hard, I might have a scenario like this. If I slam on the brakes less hard, I will have less deceleration. I have a scenario like this. If I slam on the brakes barely hard enough to achieve this scenario, that's the minimum deceleration that is allowed for this problem. So I'm going to set the final position of the car and the final position of the cow to be the same. So these two quantities will be the same. And I'm just going to call that x final. I'm not going to write x car and x cow. They will be the same position, so I'm just calling it x final. Okay, what time will this occur at? Well, we don't know. So we are now in a position to begin actually solving this problem. So I said that we have two objects that are moving. We have a car and a cow that are moving. So I will have two sets of equations that I need to consider. I will have the trajectory of the car, which is the position of the car is equal to, the final position of the car is equal to the initial position of the car plus initial velocity of the car times time plus 1/2 acceleration of the car, t squared. And if I could also talk about the trajectory of the cow. And that could be written as the final position of the cow is equal to the initial position of the cow plus the initial velocity of the cow times time plus 1/2 a acceleration of the cow times t squared. Now, when I do example problems, I first like to write out the equation with every term in it. You can look at this equation, for example. You know the acceleration of the cow is 0, and anytime you multiply by 0, that gets rid of everything here. But I like to write out the entire equation with every symbol in it, and then in the next line I plug in 0. It just, that way, like I said before, don't try to solve everything at once. Do your problems in short steps. That just helps keep your mind organized. So I highly recommend you do something like that. So let's see what we got going on. I'll now plug in equations for this. I do not know the final position of the car. I could write it as x final. Okay, I'll do that. So I could write x final is equal to the initial position of the car is 0. The initial velocity of the car is 30. I do not know what time the car comes to a stop, but that will be the final time. I do not know what the acceleration of the car is, so I'll write a car. And again, I do not know what time is. Now let's look at the trajectory of the cow. Let's see what we could plug in. So the final position of the cow, I can write as x cow. The initial position of the cow is 100 meters. The initial velocity of the cow is -5. So -5 times t for time that the car and the cow are at their final position. And then the acceleration of the car is 0. So I just get +0. And I accidentally wrote x cow again. I meant to write x final. So at this point, I simplified some of what I have to do. Now, the final position of the cow is the same as the final position of the car. Whenever I have an equal sign, whatever this is equal to, whatever this is the same as all that. Whatever this is the same as all that. If this and this is the same, that means all this must be the same as all that. So I'm going to set x final equal to x final, which is like saying all this stuff here is equal to all this stuff here. So if I set the final position of the car equal to the final position of the cow, that's like saying 30t plus 1/2 a car t squared is equal to 100 minus 5t plus 0, which I didn't include. Okay, so at this point, I have one equation and I have two unknowns. So we cannot solve it quite yet. We need more information. So let's think about what the other equations that we have at our disposal in this chapter are. We have x equals x naught plus v naught t plus 1/2 at squared. We have v equals v initial plus at. We have v squared equals v initial squared plus 2a x final minus x initial. I am allowed to use any of these equations. There's no guarantee that one particular equation will work, but if it doesn't work or it doesn't provide something useful to me, then I'll try something else. Also, all three of these equations could be applied to the car, and all three of these equations could be applied to the cow. And you have to enter the car terms when you're talking about the trajectory of the car. You have to enter the cow terms when you're talking about the trajectory of the cow. So, if the car just barely came to a stop, I'm going to set this equation aside for the moment. We'll come back to it. If the car barely came to a stop, that means v car final is equal to 0. And let's use the final velocity of the car is equal to the initial velocity of the car plus acceleration of the car times t. So let's plug numbers in. Let's see if we could get something useful. So final velocity of the car is 0. Initial velocity of the car is 30. Acceleration of the car, we do not know what it is. So I get plus a car, and the time that the car barely came to a stop, I don't know, that's t. So did this equation provide something useful to us? Yes, it did, because this here is one equation with two unknowns. Now I have two equations with two unknowns, and this system of equations is solvable. So I don't need this picture anymore. I have more room to spread out. So what we need to do now is we just solve the system of equations and find the acceleration of the car. So let's begin by using the shorter equation. I think this will be easier because I see it would be kind of easy for me to solve for a car and t here, depending on which I want to do. Here I have squares and more terms, so I'll put off solving that one if I can. So what I want to do is, at the end of the day, we want to find the acceleration. So before I find the acceleration, I'm first going to isolate t with this equation. So if I write 30 is equal to, if I write 0 is equal to 30 plus acceleration of the car times time. At this point, because the car is the only thing with acceleration, I'm going to stop writing the subscript just because it's going to be annoying. So I could subtract 30 from both sides, and I get negative 30 is equal to AT. And so I could write T is equal to negative 30 over A. Okay, so I'm going to take this piece of information and I'm going to plug it in everywhere I see a time, namely there and there. So when I write this equation now, I could write it as, oh, and there's another T right there. And I had to stop the previous video because I got to the end of the problem and realized I made a mistake somewhere. It happens to everyone. Don't worry about it. Don't let it get you down. Practice. That's the best way to learn this material. So I'm going to take this line and I'm going to write out the entire line just to make it longer, just to make it a bit neater. And then we are going to continue. So this line is 30 times t plus 1/2 AT squared is equal to 100 minus 5t. Everywhere I see t, I'm going to plug negative 30 over a into the equation. Also, I don't feel like writing a car over and over, so I'm just writing it as a. Okay, 30 times t, so that's 30 times negative 30 over a plus 1/2 times a negative 30 over a squared, because I have a t squared, and then I have 100 minus 5 negative 30 over a. Now I'm going to multiply some things through. 30 times 30 is 900. So this first term will be negative 900 over a plus 1/2 times a. When I square this term, I square both the upstairs and the downstairs. Negative times negative will give me a positive. So I have times 30 times 30 is 900. A times a is a squared. So 900 over a squared. That is a 9, that is an a. And then I get equal to 100. Negative 5 times negative 30 is positive 150. So plus 150 over a. And now I did intentionally take an extra line to first solve the term in parentheses. Now I'm going to multiply the 1/2 a into it. So I will have negative 900 over a, negative 900 over a. 1/2 times 900 gives me 450. A over a squared gives me just 1 over a. So I will get plus 450 over a. And then I'll just rewrite this term here. 100 plus 150 over a. Now at this point, we are just trying to solve for the acceleration of the car. I think the easiest thing we could do would be to multiply both the left and the right side by a. There are several ways we could solve this problem, but I think this will be the quickest. So I will multiply the right side by a. If you do something to one side, you gotta do it to the other. So I'm going to multiply the left side by a as well. Now, when I factor in the a to both terms, this will be negative 900a over a, 450a over a. So these will cancel. And I could write the left-hand side as negative 900 plus 450. On the right-hand side, I have 100 times a. I don't have anything to cancel this a with, so 100a And 150 times a divided by a, this a will cancel with that a, so I just get plus 150. So at this point, I could then say I have negative 900 plus 450 is equal to 100a plus 150. So I could negative 900 plus 450, that's negative 450 minus 150 equals 100a. I added 450 to negative 900 to get this number. I brought 150 to the other side to get this number. So then I get negative 600 is equal to 100a, and I get the acceleration is negative 6 meter per second squared. So I could phrase this as saying the car must decelerate at 6 meters per second squared. The car must have an acceleration of negative 6 to barely stopping and a split infinitesimally small short time later, after the car comes to a stop, the cow walks into it. So at this point, we have completely solved the problem. I would though like to point out that in problems like this, there sometimes are multiple correct ways to do the algebra. If you're ever asked to solve a problem on a homework or an exam, you will not need to show several correct methods unless you're explicitly asked. Just show one correct method, and as long as everything's good, you'll be just fine. A different way we could have solved for the acceleration is when we got to this line here, we could have said, okay, negative 30 equals acceleration times time. So I'm going to divide both sides by time and write negative 30 over t is equal to a. Now at this point, my two equations with two unknowns are here and here. So I'm going to take this result for a and plug it in right here. So this equation could be rewritten as 30 times t plus 1/2 acceleration, negative 30 over t times t squared is equal to 100 minus 5t. Now at this point, I will multiply this term through, so I get t squared upstairs and a single t downstairs. 1t downstairs will cancel with 1t upstairs, and then this term will be 1/2 times negative 30 times t. 1/2 times negative 30 is negative 15, negative 15 times t, negative 15t. So this term will be minus 15t, and then here I have 30t minus 15t that we found equals 100 minus 5 times t. I could then, 30 minus 15 is 15, so 15t equals 100 minus 5t. I could add 5t to both sides, plus 5t. And then minus 5 plus 5, that cancels. 15 plus 5 is 20. I get 20t equals 100, and t is equal to 5 seconds. So if the car decelerates at the minimum amount to barely come to a stop before hitting the cow, it will have decelerated for 5 seconds. Now I will take this result and plug it in up here. This is a new piece of information we have at our disposal. So I'm going to take this result and put it in right there to find out what that amount of deceleration is. So if I say a equals negative 30 over 5, because I found 5 seconds over there, 30 over 5, I get a is equal to negative 6 meter per second squared. So again, we used a different method for solving the algebra of this problem to find the minimum deceleration where the car barely comes to a stop before hitting the cow. So I would like to say a few things. One, don't worry about making mistakes. I made a mistake earlier in this problem. Don't let it get you down. Just practice, have a good attitude, and reach out to me if you have anything you want to ask about. I will take the time to help you, make you comfortable with this material. Number two, there could be several correct ways to solve a problem. So don't think like you have to use the same method that I use. As long as your method is logically consistent, you're going to be okay. And three, when you're solving these problems, write out every step along the way. If you have to spend 2 entire pages full of lines of work, but you get the correct answer at the end of the day, that's just fine. Paper is a lot cheaper than your tuition. So use all that paper to make sure that you are understanding and learning the process while you're working through it, while you're practicing. Don't try to skip steps and do many steps at once.